Let us start. Let us start. Yesterday, I have gone through. Just 1 second, please. Yesterday, we have what we have devised is first we have gone through the relation between the tensile stress as well as tensile strain and shear stress as well as the shear strain itself. What is shown here, the shear strain gamma xy x dash y dash, which is already revised in our chapter 4 strain, and this is the relation we have got for shear stress. Shear stress resulting in the shear stress in tau xy xy dash. So what we are finding from this relation is epsa 1 by 1 plus epsa x dash plus 1 plus epsa y dash. Here epsa x dash, we have told that it is extremely small in comparison to A itself, extremely small in comparison to 1, and epsa y dash is also extremely small in comparison to 1. So we are thinking this portion 1 plus epsa x dash and 1 plus epsa y dash equal to 1 itself. Here we have devised one equation that nx1, nx2, ny1, ny2, nz1, nz2 is the reduction cosine of our coordinate system Ox dash, y dash, z dash with the original coordinate system Ox, y, z, and where Ox, Oy, and Oz are along the three principal planes as per our earlier definition, because we have reduced that every point should have a position where there exists a principal or maximum or major or intermediate stress, and which are acting on such plane where there is no shear stress exists. So the plane formed by these coordinate Ox, Oy, and Oz has no shear stress. But if we have kept the same origin or the same point as O and introduced a different coordinate axis, which is Ox dash, Oy dash, and Oz dash, or Ox dash, Y dash, Z dash, then this particular plane, where the newly constructed coordinates, orthogonal coordinates, should have shear stress and shear strain, as well as tensile stress and tensile strain itself. Here, the shear stress in x dash y dash plane, shear strain in x dash y dash plane in this newly formed coordinates is given by this equation, where nx1, nx2 is the reaction cosine of the angle of the axis Ox dash with original Ox, Y, and Oz, and ny1 is the same for y axis, y dash axis, and nz1 is the same for z axis. Similarly, for Oy axis or y dash axis, we have the reaction cosine ny1, ny2, ny3, etc. Here we know that the multiplication of the reaction cosine nx1 and nz1, ny1 into nz2, and nz2 and nz2 are equal to 0, as they are mutually perpendicular to each other, or their orthogonal coordinate axis. So from this equation, what we find, this value is equal to 0 from this here to here, and this value is equal to 1. This equation reduced to n gamma x dash y dash is equal to 2 nx1 nx2 into epsilon 1 plus ny1 ny2 epsilon 2 plus ny1 nz2 epsilon 3 itself. Now, what we know from the equation 4 to 4a, we have reduce the value of sigma 1, the principal strength, sigma 2, and sigma 3, three principal strength in terms of the actions like this. Now, we have got this, just 1 second. Yes. From this here, what we found is the stress sigma 1 in the direction we know will become sigma 1 a plus a into epsilon 1, b into epsilon 2, plus c into epsilon 2. And we are put different alternatives to reduce this number of constant a, b, c, etc. by putting by using the conception of isotropic force, which means the force at a particular point is uniform in all direction itself. And as it is uniform, the forces are uniform in all directions. The strain constant with these forces also equal. So we can safely say that due to the action of the force sigma 1, say along x-axis, the direction of epsilon 2 and epsilon 3, which are say along y-axis and z-axis, and both are at right angles to alpha, must be same for isentropic material. So we are saying there is no b and c, but only b. So a multiplied by epsilon 1 plus b multiplied by epsilon 2 by epsilon 3, epsilon z epsilon 2 by epsilon 3. So if we add a term minus b epsilon 1 and plus b epsilon 1, what we do, the equation will take the particular form a minus b into epsilon plus b epsilon 1 plus epsilon 2 plus epsilon 3 itself. By adding and subtracting the by the epsilon like this, but you know, in the theory of fast invariance, that epsilon 1 plus epsilon 2 and epsilon 3 is equal to either J1 or the cubical dilation J delta itself. So we know we denote b by lambda and a minus b by 2 into mu. So the equation has become sigma 1 lambda into delta here and 2 into sigma 2 here there is a 2 value into epsilon 1 itself. Here a minus b we are denoted by minus 2 into mu. So here a minus b we are putting 2 into mu here, thus it becomes 2 into mu into epsilon 1 and x plus y plus z we put delta and b is equal to lambda. It's b is equal to lambda and x plus y plus z is equal to delta itself. So the stress will reduce to a form epsilon delta 1 is equal to epsilon into delta plus 2 into epsilon into 2 into mu into epsilon 1 itself. Similarly, other stresses, other principal stress sigma 1, sigma 2, sigma 3, we get the same value itself. So we got the three equations, delta 1, delta 2, delta 3 from this explanation itself. Now, what we do here, we put this value of delta 1, delta 2, and delta 3 from equation 4a to b into equation 4.6b itself. Hence, what we do, we replace sigma 1 by this value, delta into lambda into delta into 2 into mu epsilon 1 plus ny 2 here. We are putting in equation. This is not in the equation, but in earlier equation, the earlier parts are just in the earlier page. ny1 to ny2 lambda delta plus 2 into mu into epsilon 2 nz2 nz1 z2 multiplied by lambda. This third equation, lambda into delta plus 2 into mu into epsilon 3. So we got tau xy x dash y dash with this equation means the shear stress in x dash y dash plane, x dash shear stress along x dash along the axis OX dash, which is actually the normal to the planes x dash y dash itself, normal to the plane y dash z, and which is pointing towards y dash is equal to given by this particular equation itself. And if we again simplify the matter, we'll find that lambda into delta multiplied by this equation plus this and this one means will comes here again, and 2 into mu will take this from nx1 into nx2 epsilon 1, ny1, ny2 epsilon 2 plus nz1 and nz2 epsilon 3 itself. Here we again know this is this portion is equal to 0, and 2 into mu into epsilon is given here as gamma x dash y dash. So tau x, if we put the value of gamma x dash y dash here, this equation will take the form tau x dash y dash is equal to mu gamma x dash y dash. Means this is the shear stress in x dash y dash plane, which is equal to which is equal to the shear strain in x dash y dash plane multiplied by a factor mu itself. Now we know here from this equation 8, the rectangular shear stress component tau x dash y dash with the rectangular shear strain component gamma x dash y dash, the relation between here this shear stress and shear strain itself. And we know from the elementary strength of material that mu is equivalent to the modulus of rigidity or is divided by G. So here we have reduced the same equation of the relation between the shear stress and shear strain as per the Hooke's law, which are proportional to each other, and which is equal to shear stress is equal to a constant of proportionality known as modulus of rigidity multiplied by the shear strain itself. And here we can follow the same thing with another axis OZ dash. So far we have taken OX dash and OYZ. And if we take the third coordinate axis OZ dash with direction cosine nx2, ny2, and nz3 at right angles to OX dash and right angles to OY dash, so that the orthogonal coordinate system O dash, OX dash, Y dash, Z dash forms. So one can get the equation similar to earlier equation 6 and 6a and b, like sigma y dash, sigma z dash is given by nx2 sigma 1 ny2 square sigma 2 and z2 sigma 2. Same is the case with nz z1, and same is the case with tau yz xz, where nx2 nx3 into sigma 1, nx2 nx3 into sigma 2, and so in sigma 3 itself. Just 1 second. Only 3 participants. One second, please. So here tau in shear stress in z dash x dash plane is given by this particular formula nx3, nx1, sigma 1, ny3, ny1, t1, and so and so. So similarly, in like another direction, we can form that epsa yy, epsa zz is given by this nx2, epsa 1, ny2, epsa 2 whole square, nz2, epsa 2 whole square, epsa 3 itself. And now, epsa zz is given as nx3 square epsa 1 and y3 square z1 and x square z2 itself. And gamma shear strain in yz delta plane is given by the equation, this one question, and yz dash is or gamma itself is also shear strain in z dash x dash plane is given by this particular equation itself. So from these three equations, we know sigma x dash is this one, and if we put the value of sigma 1, sigma 2, and sigma 3 like our from equation 4, we'll take this particular form lambda x plus lambda into delta plus 2 into mu epsilon x dash y dash itself. Now, similar to itself and x dash y dash also similar fashion will come here. So we are getting tau x dash y dash and tau y dash z dash, tau z dash in terms of the respective shear strain in multiplied by the factor mu, which is equivalent to our shear modulus of rigidity itself. So all this equation relates that three rectangular stress components in three rectangular stress components means three rectangular stress components means three stress components as sigma x, sigma y, and sigma z. Means stress component along x direction, y direction, or z direction, which is also we are saying that principal stress component in sigma 1, sigma 2, and sigma 3 in six rectangular as well as six rectangular strain components means stress component and six rectangular strain components, which includes the tensile strength as well as shear strength. And in this, we are having out of 36 constant itself, which we have taken a particular decision that we will consider only isotropic material. And if we want to do consider the stress condition of stress and strain condition of a particular point itself, it will take the position and we take this position as all the stresses in all three mutually perpendicular directions are same. To take this proper as a yes, let us go for the next page. Let us go through, let us discuss the bulk modulus. Now, we have got the equations 11a and 11a to c. We are adding these three relations. What we have, what is 11a and c? Let us go through first, understand. This is 11a, 11b, and 11c. This is the equation is sigma x dash is equal to lambda into delta plus mu into epsilon x dash y dash, and sigma y dash equal to lambda into delta plus 2 mu into epsilon y dash z dash, and sigma z dash equal to lambda into mu into lambda plus 2 mu plus epsilon z dash s dash itself. If we add all these things together, all these three equations, this one, and this one, it will take this particular form. Now, we have sigma x dash plus sigma y dash and sigma z dash is equal to 3 into lambda gamma, because we know the lambda gamma is the same everywhere. At present, in all these four equations, 3 into lambda gamma plus 2 into mu into e xx dash plus e yy dash and e z dash. Now, from our equation on and from our theory of invariance of stresses, we know that this summation sigma x1 x dash sigma y dash plus sigma h dash means stress along OX dash, stress along OY dash, and stress along OZ dash is equal to L1, which is also equal to sigma 1, sigma 2, sigma 3, which is the principal stress, and stresses along OX, OY, and OZ. So here, multiplication of these three factors are equal to each other and equal to as per our first variant of stresses, and that variant is equal to L1 itself. And epsa x dash, y dash, epsa z dash dash is equal to G, J, or second variance of stresses, which is also equal to, again, epsa 1, epsa 2, and epsa 1 plus epsa 2 plus epsa 3, because it is individually the principal strain in x-axis, principal strain in y-axis, and principal strain is z-axis itself. Now, so equation, this particular equation, we can write down as like this. Sigma, first of all, sigma 1 plus sigma 2 plus sigma 3 is equal to 3 into lambda plus 2 into gamma into delta, which is equal to J1 or third J1 as well as cubical dilation, which is called capital delta itself. Or we can same thing, we can read there as like this. This one is equal to 3 into plus lambda is equal to delta, as well as L1. We can put L1 here as 2 into lambda plus 3 into mu into J1 itself. So three-way in equation 13 can be written here. That is 13 B, C, and C3 equation we have formed. Now, if we know the volumetric strain, just 1 second, please. If we know the volumetric strain, you know, if delta is the volumetric strain, the rate of change of volume in terms of the divided by the original volume itself. So what will happen? We just 1 second. What will happen like this? What we'll find from here, we know K is equal to pressure multiplied divided by volumetric strain is equal to pressure. If pressure is P, generally we assume this pressure P is uniform in all directions itself. Now, that is sigma 1, sigma 2, and sigma 3 is equal to P. We see there's principal stresses, maximum, intermediate, minimum, they are all same here. Here we are assuming to get the volumetric strain itself. Then what will happen? 3 into 3 divided by P itself, 3 divided by P divided by delta is equal to 3 into lambda plus 2 into mu itself, or which is equal to K. P by delta is equal to K lambda, so this is equal to 1/3 3 into lambda plus 2 into mu itself. Thus, the bulk modulus of isotropic solid related to the Lami's constant through equation 14. So what is the bulk modulus? It's like this. Which is K, which is related to the Lami's constant delta as well as the mu itself. Now, the Young's modulus and Poisson's, let us find out the Young's modulus and Poisson's ratio itself. Now, what will happen? Now, what will happen? This the delta is equal to sigma 1 plus sigma 2 plus sigma 3. We know we put the value of 3p itself divided by from here, just early part of this equation. The delta is equal to sigma 1 plus sigma 2 by sigma 3 divided by 3 into lambda plus 2 into p itself. Actually, it is the total force multiplied by the K itself. So from the equation, we have the value of delta, equation 13b here, which is 3 into P. 3 into P is equal to sigma 1. We put it sigma 1 plus sigma 2 and sigma 3 and then get delta divided by all three of them by this 3 by lambda plus 2 mu. So we have got this type of equation itself. Now, if we put this value of delta in equation 4a, that is, substitute this value of delta in equation 4a, which have the equation the formation sigma 1 lambda into delta plus 2 into mu into epsilon 1. Then in place of delta, if you put, it will take this particular form. Sigma 1 is equal to lambda divided by 3 into lambda plus 2 into mu multiplied by sigma 1 plus sigma 2 and sigma 3 plus 2 into mu into epsilon 1 itself. So we have, after taking certain simplification, we will have epsilon 1 like this, lambda plus mu multiplied by mu multiplied by 3 into lambda plus 2 into mu, whole multiplied by sigma 1 minus lambda here by 2 into lambda plus mu into lambda plus lambda 2 plus lambda 2 itself. Now, we know from the elementary strength of material, epsilon 1 is equal to 1 by E multiplied by sigma 1 minus gamma into sigma 2 plus sigma 3 itself, where gamma is the Poisson's ratio and E is the Young's modulus or modulus of strength, modulus of rigidity in tension itself. So, Young modulus and Poisson's ratio, if we compare this particular equation with this particular equation, hence equation 15, what we'll find, this portion lambda plus mu divided by mu into 3 lambda plus 2 mu is more or less similar to 1 by E itself. And this lambda divided by 2 into lambda plus mu, which is equal to similar to gamma itself, because we have this sigma 1, here sigma 1, sigma 2 plus sigma 3, sigma 2 plus sigma 3 is equal to, and looks here is also matching here and matching here itself. So we just put down if epsilon is just reverse of this fraction, 3 into 2 3 lambda, mu into 3 lambda plus 2 into mu thereby lambda plus mu, and V is equal to here lambda divided by 2 into lambda plus mu. So we have got a relation between the Young's modulus and our Lami's fraction term lambda and mu, and Poisson's ratio with Lami's fraction lambda and mu itself. Now let us find out the relation between them itself, the relation between the elastic constant itself. We know, we are familiar with the Young's modulus E and Poisson's ratio gamma. We know what is Young's modulus. Stress is proportional to strain in or the longitudinal direction, where constant of proportionality is equal to epsilon, provided the stress is within the elastic limit. Same is the case of Poisson's ratio, lateral strain divided by longitudinal strain within when the strains are within elastic limit itself. Now, and shear modulus or rigidity, shear modulus or modulus rigidity G, you know, shear stress is proportional to shear strain within the elastic limit itself, and bulk modulus is the pressure applied divided by volumetric change itself. All these four forces are elastic moduli, altogether called elastic moduli. But among these, two are independent, and E and V are taken as the independent constant, because the bulk also depends on G itself, and bulk modulus also has dependence on G itself, but it doesn't depend on gamma itself. So in other words, too, G and K you can expect in terms of E and Poisson's ratio, as we know, gamma G is equal to E divided by 2 into 1 plus gamma, K is equal to E divided by 3 into 1 minus 2 gamma itself. Now, we always taking the help of the definition of isotropic material itself, and we have reduced the 36 constant involved in general Hooke's law into only two constants, one for lambda, one for another for mu, which is Lami's coefficient, and the latter second coefficient name is similar or same as the modulus of residual J. Now, in terms of this, we can safely deduce that other elastic constants like E into mu, U, mu, and J itself. If we put the value of E as well E from the equation, if we put the value of E from equation and from this equation and put the value of gamma from this equation in this particular E and gamma, then E will take the particular form mu into gamma itself, and gamma in lambda will take the particular form lambda divided by 1 plus 2 mu itself. And from the equation of strain K itself, here we'll reduce to this one, and lambda after, and G will reduce to mu itself, and lambda will be equal to V into E divided by 1 plus gamma minus 1 plus 2 mu itself. It should be observed that equation 17 means from here that the bulk modulus must be positive itself. Bulk modulus means K, the ratio of bulk modulus ratio of volumetric strain divided by the ratio K itself. 1 second. The pressure divided by the volumetric strain here. Here, if we from the relation itself, what is clear? If the Poisson's ratios cannot exceed 1/2, or in that case, this volumetric strain will be negative. Means there is no increase in bulk modulus, will become negative, which cannot be. So the maximum volumetric strain will be equal to 1/2 or 0.5. This is the upper limit for gamma itself, and for 3G, for this case, with this value of E will reduce to 3 into G, E is equal to 3 into G, and K will become equal to infinity itself. If it is exactly equal to 1/2, if it's less, then K will have some value, but if it is exactly equal to 1/2, this portion will become 0 and K will become infinity itself. Thus, a material having Poisson's ratio is equal to 1/2 is known as incompressible materials. Means there cannot be any change in its volume itself. Incompressible means there cannot be any change in its volume itself. It cannot expand, it cannot contract, even after application of a huge amount of force itself. So, since the volumetric strain for such an isotropic metal is always equal to 0. So, as per the limit of the Poisson's ratio, mu is equal to J, this volumetric ratio strain for isotropic material for the case is 0. Means in all direction there is no strain, no stress developed, no change in stress, and no change in strain, or no change in length. So, in terms of principal stress and principal strain, if we put that equation number 4, it will take this form sigma 1 and epsilon 1 here with the principal stress in one direction or x direction, sigma 2 and epsilon 2 principal stress in y direction, and sigma 3 and epsilon 3 principal stress in a direction itself. And we know from our theory of invariance, delta 1 is the multiplication of epsilon 1, epsilon 2, and epsilon 3, which is also called J1, a second variant of stress itself. And in our last page, what we have found, we have got the value of epsilon 1, epsilon 2, epsilon 3 in this form of this equation in terms of sigma 1, sigma 2, sigma 3, sigma 2, sigma 3, sigma 1, and sigma 3, sigma 1, sigma 2 itself. So we get what epsilon 1, epsilon 2, epsilon 3 in terms of sigma 1, sigma 2, sigma 3. And if we take the rectangular stress and strain components referring to an orthogonal coordinate axis OX, Y, Z, or that's sigma x, which is not our principal stress axis itself. Sigma x, sigma y, sigma z take this particular form, epsilon xx, epsilon yy, epsilon zz itself. And in the same equation, from the same equation as above, and with delta is equal to j is equal to fx plus uy and zz, and tau xy mu into gamma xy, tau yz mu into gamma yz. Hence, this is the shear stress in yz plane, shear stress in xy plane, and this is the shear strain in xy plane and shear strain in xy plane, and this is also shear stress and strain in yxz plane respectively itself. So f psi f6 is equal to f psi f6, same equation we are just using here. We are just replace epsilon 1 by epsilon x6, epsilon 2 by epsilon yy, and same with sigma 1, sigma x with sigma 1, sigma 1 with sigma x, sigma 2 with sigma y, and sigma 3 with sigma z itself. So this will be equal to sigma 1, sigma 1 minus sigma 2 minus sigma 3, and sigma 2 plus sigma 2 x itself. And we also got the gamma x1. Gamma x1, we can convert it to 1 by b into tau xy, gamma yz, 1 by b into tau yz, and so and so. So in the preceding set of equations, lambda and mu are Lami's constant in terms of both familiar constant. The shear stress relations are like this. If we get familiar reaction constant epsilon for Young's modulus and V for the Poisson's ratio, we can write it like this. Sigma x, we replace it by lambda. Sigma x, we replace it equal to lambda plus mu equal to, because we have find it similar. Sigma x becomes E epsilon by 1 plus gamma plus 1 minus 2 gamma into delta. We are putting the values, respective values, which have reduced, and got this particular result. Sigma is lambda into G1 and plus 2G into A epsilon XX. Similarly, epsilon Y, we are already formed this equation here.